All right, guys, welcome back. If you could, please, of course, turn your cameras on so that it's not so long here. Now, we spoke about probability as a sequence, and I hope you understood the meaning. And now we talk about an axiomatic approach for those very same ideas. Now, when we have an axiomatic approach, what we have now are very definite results, but the results no longer necessarily mean anything. So this is the usual dilemma you have. You can be certain of something, but have no idea what you're certain of, or you could understand something, but not be certain of what you understand at all. And that's what we are facing. So the axiomatic approach defines or begins to work as follows. So first you have this idea of a sample space, and you should think of a sample space as the collection of all possible universes. So whenever you are creating a simulation or an experiment, there is going to be one universe that comes into being. So to make it simple, when you roll a die, we're going to actually make it later more substantial or complicated. But for now, we imagine that the universe consists of the die showing either the number 1, 2, 3, 4, 5, 6. Yes? So that's the collection of universes. When I say 1, I mean everything around us. Birds are flying, trees are green still or becoming yellow, but the die is showing the number 1. So that means everything in the universe, but the die after being thrown is 1. Everything in the universe, but the die being thrown is 2, and so on. Now, when you are simulating a flashlight, that's a sample space might be the lifetime from 0 to infinity. Yes? So then any subcollection of universes is known as an event. An event is just a subset of S for our purposes. It's not precise, but for our purposes, an event is just a subset. So for instance, the event that the flashlight lasts longer than 5 hours is the interval 5 to infinity, which is a sub-interval from 0 to infinity. So with the die, we can find the event that the outcome is an even number, that is 2, 4, 6, or the event that we have division by 3. In other words, that the outcomes are 3 and 6. So an event is just some collection of particular possible universes, whereas the sample space is the collection of all universes altogether. Good. Now we can form intersections of events. So for example, the intersection of even outcomes and divisible by 3 is just the outcome 6. We can form unions. So even and divisible by 3, it's all the possibilities here. It could be that the empty set, that's also a subcollection of universes, the empty subcollection of universes. Yes. And we have the complement. So the complement of an event E within S, it's collecting all the outcomes in S that are not outcomes of E. So I hope you understand those theoretic notations and what they mean, right? So then we have the following very simple propositions. They are very logical, and I will just mention briefly what they mean. So the complement of a union is the intersection of the complements. Why is that the case? Well, what does it mean, guys? The complement of the union means that we're gathering all outcomes that are not in any of E1, E2, E3, all the way to En. If those outcomes are not in any of the ENs, that means they are not in E1, and not in E2 and not in E3 and so onwards. So you can see that those sets logically have to be the same. It's known, I think, as De Morgan laws, but you can understand why that set notation is correct. And we have notation when we have situation number 2, and that's the complement of an intersection is the union of complements. Now that's also very simple to understand. If something is not in all E1, E2, E3 and onwards, then it's not in one of them at least. Yes? So if it's not in E1 and E2 and E3, then it's not in E1 or not in E2, or when you use the word or, that's a union. Or gives you more possibilities. And means that two parts of the and have to be true for this to work. And now we are ready to describe the axioms of probability, guys. So same thing. You remember we talked about a sequence last time. So I think usually when I try to understand probability, I imagine that there is a sort of balance in nature. Give nature an opportunity, enough opportunities, and it displays its preference. So a simple example was throwing the die, right? Why would I conclude that a fair coin has probability 1/2 of coming heads? That's because when I toss it all the time, continuously toss it again and again and again, and measure the ratio of successes with all the times when I got heads divided by total number of trials, I will get the limit approaching to 1/2. So we think of probability as a sequence, as a limit of a sequence. Now here, we simply abstract and we say probability is a function, right? So it's an abstraction that logically makes sense. Why is that a good definition? You have to think of it. So probability is a function from the power set of the sample space. In other words, it's a function that takes every subset of the sample space, yes, and makes it into a number between 0 and 1. So this function satisfies the following axioms. Axiom number 1 is that any event you take, its probability is between 0 and 1. Makes sense, yes? The other axiom, axiom number 2, is that probability of the sample space is 1. You can see that at least some of it makes some intuitive sense, right? So the probability that at least one universe, if I gathered all the universes that could possibly come into being, and I run the experiment, at least one of those universes will come into being. That's why probability of S is 1. In terms of sequential approach, it seems natural that to be the case. And the last axiom, axiom number 3, is the most difficult of them all. It is the reason why we need to use infinite series very frequently. So what happens here? If we are having infinitely many, a sequence of countably many disjoint, pairwise disjoint events, that means that all the universes in E1 are entirely disjoint from universes in E2, so on, right? Then the probability of the union of those events is the infinite series. That's the summation of the probability of each of the events individually. You understand? It's also somewhat natural, but the axiom is stating that specifically for infinitely many events. So today we begin, well, first we'll make a few remarks, right? So I already mentioned what's axiom 3. And B, I should tell you this, guys, that as it happens, if S is big enough, then it is impossible to define such a function. So when I said every subset is an event that has a probability, that is not true. And I'm just mentioning it to you now because perhaps you will accuse me of being a liar years later, right? You'll think, why was he lying to us? Why was he giving us incorrect information? You would probably not notice that, but there are always subsets that do not have measure. That's, you know, in real analysis, that do not have probability. I gave you some constructed example of how such a thing might look like, but you have examples from mathematics. There are things that do not have probability, And maybe it should not be strange. To me, it's stranger that things actually do have probability. You understand? Because having probability means that there is regularity. Not having a probability in terms of a sequence means that every time I start the sequence, I will have an entirely different result. I toss a coin, and every time I calculate the ratio, it doesn't appear to go anywhere, right? At one time, it's 7/10, then maybe 7/100, and then 99/100. You understand that it just moves all over the place. That might be just as natural. Why should a sequence converge? You know of non-convergent sequences, you've studied such. So to say that there would be things that don't have probability is very similar to the claim that there would be sequences that do not converge. And in neural analysis, it means areas or regions that do not have area, more so, right? The regions that are bounded in some sense, but do not have area. You cannot describe an area, properly speaking. Good. So all of those are very interesting concepts. Good. And maybe one other thing I should mention, I'm not sure if you're interested, when I mention the word remark, there is this pressure in my head, and I have to mention my favorite writer, the German writer Erich Maria Remarque. Do you know him? And you might know of the book All Quiet on the Western Front, and that's not a very good book, in my opinion. That's when he was young when he wrote it, one of his first. But a very good book is Three Comrades. If you have a chance, read the book Three Comrades. I even have a copy in English. If you're interested, I can send it to you. Now, back to the topic. What is the probability of the empty set, guys? What do you think is the probability of the empty set? I want to see if you have a good guess, and then we are going to justify it. I'm not always tricking you, right? So what's the probability of the empty set? Yes, the axioms are here. The first is that no subset of S has a probability bigger than 1 or less than 0. The second is that the probability of the full sample space is 1. And the last is a probability on how to calculate it for disjoint events, infinitely many disjoint events. Yes? So not everybody replied. I've seen very feeble 3-4 replies. I am not engaging you enough. The probability of the empty set is very naturally 0, right? Because when we run an experiment, the universe, S is the sample space, it is the collection of all universes that will come into being, which means that when the experiment is carried, one of those universes should come into being. When you toss a die, something should happen, right? Either 1, 2, 3, 4, one of those numbers will be displayed. So the empty set should have probability 0. And here is one quick way to understand why. Now, the empty set is, well, it's empty. So I can label E1 as the empty set, and E2 as the empty set, and E3 as the empty set, and so on. I can use axiom 3. Do you understand, guys? That the union of empty set with itself infinitely many times forms a mutually disjoint sequence of events. Do you agree? Because intersect emptiness with emptiness, you don't find an event in S. You don't find anything common. There is no common event in S that's in here, in this empty set, and in this empty set. Yes? So they are disjoint. Do you agree? So then I can apply very simply axiom number 3. I can do something else if you want to. I solved it 2 ways, but I'm just right away doing axiom 3. And I see that the probability of the empty set is the summation of the probabilities of the empty set. Now, the probability of the empty set is supposed to be defined based on the description. It's supposed to be a number between 0 and 1. Yes? Now, if it is a number between 0 and 1, it must be equal to this infinite series. Notice, guys, that P of empty set is the same number. Do you remember when an infinite series converges? Yes? Would anybody tell me in the comments very quickly what's a requirement in terms of calculus for an infinite series to converge? No, do you remember what convergent means, guys, right? So we gave you, yes, here we have. Very good. Camille, you said exactly what I was hoping to hear. So what must be the case, that's called the divergence theorem. It must be the case that the sequence of terms that you're adding up, that sequence has to go to 0. Remember, guys, how we did it, right? Infinite series are defined this way: A1 plus A2, A1 plus A2 plus A3. I don't look at the infinite sequence in calculus. I don't do that. So I just define it as a limit of partial sums. Now, the only way this limit can exist is if the gap between S1 and S2, between S2 and S3 and onwards, if the gap is decreasing to 0. That gap between S3 and S2 is A3. Between S4 and S3, it's A4. So that gap is the sequence of elements that you're adding up. That must disappear to 0. Otherwise, convergence will not be possible. Do you agree? Otherwise, S1 and S2 and S3 and S4 will not start looking like that same number if you write it in a long column. Good? So, and this is a constant term. You understand, guys? The sequence here is P empty set, P empty set, P empty set. It's the same number. I'm adding the same number again and again to itself, and I have to have something convergent. How can that happen? Only if that number is 0. Do you agree? Because the only way a constant sequence is, its limit is 0, is the term that I'm adding up is 0 to begin with. Did you understand? Now I have to see a lot of yeses, guys, right? And if you're too lazy to write a yes, you can write a Y.
I'm too lazy to write a Y.
Good. Let's move on. So then, guys, we know that the empty set is the probability of the empty set is now 0. Now we are going to solve for the probability of a finite union, E1 union E2, right? Axiom 3, if you look at it carefully, if you follow by axioms, if you're following logically but blindly, right? You're not interpreting. Infinite sum, you can partition it if the events are disjoint, mutually disjoint, but you have infinitely many of them. But what do I do if I have finitely many events that are mutually disjoint, right? I cannot right away apply axiom 3. So what do? Well, I can supplant that with more mutually disjoint sets, which are all the empty sets. You understand? I can make a finite sequence of mutually disjoint events into an infinite one by attaching lots of copies of the empty set. Yes? So the probability here is, of course, the same. If I attach copies of the empty set, I'm not changing anything. And this by axiom 3 I can make into an infinite sum. And this infinite sum I can break into this head and this tail of the series, where the tail of the series is just adding up the empty sets. Yes. So that is just 0. So I now see that for finite sums, it works all the same. Next, guys, do you want to try the next one, or do we move just on? I want you to show, or I will do it, the probability that E complement is equal to 1 minus probability E. Yes.
I think we say that since PE is bounded between 0 and 1, then P of the complement of E would have to be less than that. So it would have to be 1 minus PE, just the only value we could have.
Well, I mean, you have to argue with axioms.
Then we would be using, well, under axiom 1.
Well, axiom
And
1
axiom
is
2.
only saying that that this is also between P of E complement is between 0 and 1. It doesn't tell us how to calculate it, right? It doesn't tell us that it's 1 minus. Yes, it just tells us yes, it's true that if this formula is true, it's not violating axiom 1, but it's not following from axiom 1 that's what you can do. Okay?
Sorry, these proofs are my least favorite part of real analysis, and I never got any of them right. So I'm just going to.
It's okay. It's probability, not real analysis, but
the math is the same.
Similar. Yeah, it's very similar. Math is exactly the same. I agree. All right. I'm sorry I give you so little time to think, guys, but I'm trying to learn from my mistakes. Well, Stephen, maybe what you're saying, you can just use that and get the answer. So here is how we can approach it. So first, we can observe that S is divided into E and E complement. Yes? For any event E, that's the case. And E and E complement are mutually disjoint, which means by axiom number 2, 1 is equal to the probability of S, which is probability of E union E complement. And here we already proved we can do that also for, we can make axiom number 3 finite. It doesn't always have to be using infinite mutually disjoint sets. So we can do that. Do you see that? So we have 1 is equal to PE plus PE complement. And now it's just a simple algebra. Just move PE across and you have probability of E complement given. You understand, guys? Very good. Yes. Next is this proposition, guys. I can also show you that the function P, the probability function, is increasing in the sense that if I obtain a bigger subset of S, a bigger event, it will have more probability, or at least no less probability, right? That's called increasing property. So how does it work? Well, we are going to show that if E is subset of F, probability of E is less than probability F. And how can we do that? Well, we can just simply observe. We don't even need S here. We can just observe that if E is a subset of F, then F is equal to what? It's equal to E union E complement F. Do you agree? EF intersection is just E. And E complement F, it's whatever is not in E, but still in F. You understand this, guys? F is bigger. So I can draw you a picture if you prefer. This is what I'm talking about. So here is F, right? And here is E. So what do you observe? F is equal to E union, this here is E complement but F. So E complement and F. Do you agree? Because E is a subset of F, then that is pretty obvious. And those are disjoint events. E and E complement F naturally are disjoint, just as I drew. So I can again use that modified axiom 3 in calculating probability of F as probability of E plus probability E complement F. I do not know what's this probability, but by axiom number 1, this number is at least 0 or more, right? So that means F minus E, you can use that notation if you prefer, right? It depends what you're trying to capture. The idea is, of course, probability of E plus probability E complement F has to be bigger than probability of E, because this number that I'm hovering my mouse over is bigger or equal to 0 by axiom number 1. Yes? Complete. I'm so happy. So the next proposition, we're almost done with the propositions, and hopefully we will start with the interesting documentation, guys. So probability of E union F, it's the probability of E plus the probability of F minus the probability of the intersection. Now you can see that this is the case by using the Venn diagram, right? So you can just apply the Venn diagram if you want. Here is E. And here is F. Yes? So it's very much like probability of E union F is very much like calculating the area of E with F. So what is that? This is the probability of E plus the probability of F, except what did I do? I counted the middle region twice, right? Probability of E, I used that intersection, and probability of F, I used that intersection. So I need to remove one use of the intersection. And this is a Venn diagram illustration of why that must be the case. Of course, we like to do it by axioms, right? We want to follow the axioms, and just drawing is very nice, very suggestive, but not directly telling me which axiom was used when. But do you understand the drawing? Yes, you understand why this result is very clear. I'm going to erase it now. Now, by the definition, I can do the following, guys. I can use axiom 3 essentially if the events are disjoint. So what do? I can write this entire union as E union E complement F. Do you agree? And now they are disjoint. It's what's in E, and then everything else that's not in E, but in F. Yes, it's going to be in general, Barry, called inclusion-exclusion principle once we generalize it, right? It's going to be a very important formula. So what do we have here? We have probability E union F. It's the same as the probability of those events which are now disjoint, right? It's what's in E and then what's extra to E but is in F. So we can write the addition. Now I have to calculate this guy. Now this guy, I can recall that probability of F is the same as probability E intersect F plus probability E complement intersect F, right? So it's either that F happens and E happens, or F happens and E doesn't happen, right? So those are the two possibilities, right? You can always condition like this. And then what do? Look at it. This is the guy I'm searching for. So probability E complement F is the same as probability F minus probability EF. Here we have that line. So we just now plug it in and we have our proof complete for unions of two events. Yes? It should be simple practice, guys. It's logic. Something that in this day and age fails. So next is the union of three events, E, F, G. We can generalize it. I would just like to show you what happens with three events, and we are going to obtain a pattern. And the pattern is going to be very useful. Good. So let's see what happens with this pattern. So if I have three events, I don't have to start from scratch. I can group two of the events into one event, and then I have a union of two things, right? And that's by the formula just obtained. It's the probability of the event in red brackets plus the third event minus the probability of event in red brackets intersected with G. Yes? And then you see I underlined it in blue. This is now the same formula that I can apply from the one we derived. It's the same formula. We have two events here. So I expand it and I get this part. And so now I have to figure out how to expand this minus here. And of course, here I distribute the G. It's probability EG, FG. And I can apply the formula for the situation. Again, formula that we obtained here for two unions. And so what do we get? We get probability E plus probability F plus probability G minus probability EG minus probability FG, and then minus minus, it becomes a plus the intersection of all three of them. Yes? Now, what's the pattern, guys? Look at it. The pattern is very interesting. I add up for the union, I add up all the single events, subtract every possible combination of pairs. Do you see that? First, second, third, every solitary event is added, subtracted every pairing, and then adding every possible triple. That's the general pattern. You can convince yourself that that's the situation that's happening all the time in the general inclusion-exclusion formula. And this is that formula over here, guys. Probability of E1 union E2 all the way to En is written as this summation. And so that you're not scared by the summation, I'll tell you what it means. It means add up all the single events, probability of every single event, subtract every probability of every pairing, then add the probability of every possible triple, then subtract every probability of any combination of four, and onwards until you exhaust, until you have gathered everything. Do you understand? So for instance, here I wrote an expansion for E1 union E2 union E3 union E4. So I add up all the possible single sets, I subtract all possible pairings, I add all possible triples, and I subtract all possible combinations of four, which is of course only one possible combination of four. You understand? So you go 1, 2, 3, 4 until you reach to this union, and that you should verify on your own, right? I mean, we can discuss that if you want to, but you should know why this is true, and you should not rely on memory. You should be able to extract this formula in just a few seconds. Good. Any questions so far? Oh, by the way, just wondering. You see, you can count them, of course, but can you give me a formula, guys? Can you tell me how many possible pairings will I have? If I have 4 events, E1, Union E2, Union E3, Union E4, I don't want you to tell me the actual number that you can count with your fingers. I want you to tell me a formula. How many possible pairings of events can I have in this formula if I have to combine every possible 2? Very good, Nicholas. Do you see why that is the case, guys? What is 4 choose 2? 4 choose 2 means we have 4 different sets, and every combination means select any 2, right? So it would be 4 choose 1 for singletons, 4 choose 2 for the pairings, 4 choose 3 for the triples. That's how many we have. Can you hear me?
I can hear you just fine. Your audio, I thought it went out for a second there, but it came back.
It told me that my internet was unstable, so I don't know why. I mean, I even connected the wire, so who knows? But hopefully it came back. Yes. Mostly, guys, do you hear me well? Some of you look disappointed that you can hear me well, honestly.
It's a little bit choppy right now, but I can still hear you.
Mm-hmm. Well, we'll do our best. What can I say? I am on the cable. Exactly, right? I am on the stupid cable, which is supposed to be fast. It shows a Wi-Fi. Interesting. You're telling me that this thing decided to make it a Wi-Fi? Yes, annoying. All right, I'm going to do something dangerous. Are you ready? I'm going to disconnect. So if I lose you, you understand why. 1 second, or is it? It's supposed to be by the cables. I'll check it next time, okay? Are you there? I'm hoping it means I'm connected to that. Good that somebody has a sharp eyesight. This disgusting thing decides to twist and turn to be, no, yeah.
You are connected. We can hear you.
Yes, hopefully through the cable now, because it is supposed to connect to the cable automatically, and I didn't see that it was using Wi-Fi. Apparently now it's using the cable, but I hope it is. Regardless, I'll test it next time. All right, you can hear me clearly, yes? I hope it means that I am now connected to the cable. Well, good. Somebody has a very good eyesight, huh? All right, thank you. Yes. Good, guys. So let's now, hopefully everything is now working well enough. And here is the situation. It's, by the way, true. I know some of you have cats, right? Yes. So I have two of them. And cat A irritates me with probability 0.95%. What's that? It's the landlord just came to take away my money. I have two cats. One of them irritates me with probability 0.95. And the other cat irritates me with probability 0.01, 1%. Taking away the last penny. I tried to hide something under my pillow, but I guess he knew. Yes, I will try to put it, you know, apparently one cannot be evicted in New York, right? If one is a deadbeat, one cannot be evicted. So hopefully this is recorded and you will see, and you are my witnesses, right? You've seen that I had a pack of money in my hands and now I have no money, right? You have seen it. Well, I mean, Russian landlords don't care what they're allowed to do or not. They just show up. Anyhow, so back to this thing. Back to this thing, guys. So what's the probability that I will not be annoyed? That I will not be annoyed by any of the cats. Right? So calculate it quickly. All right, we're hopefully ready enough, guys. It's a simple question. Yes, very good, very good. You're much faster than me at those questions, I see. Very nice. So here is the situation, guys. So first of all, the probability that I will be annoyed by at least one cat is probability A union B, which is probability A plus probability B minus probability A B. And that happens to be this number here. And the probability I'll be annoyed by neither is the complement of the union, which is 1 minus the union, which is this number, yes? And this concludes this lecture, and now we can move on to combinatorial analysis again, twice. So let's consider sample spaces having equally likely outcomes. So a sample space that has equally likely outcome means that the probability function assigns the same number. Let's say if it's a finite set, it assigns the same number to each set, yes? So of course, if we have n outcomes, the probability of outcome 1 is the same as the probability of outcome 2, and it's equal to p. And by the axiom of probability, the probability of S is 1, which is the sum of all the n copies of P. Make sense? Which means that 1 is equal to P multiplied by n, which means P is equal to 1 over n. So far, that must be very clear. Yes, guys?
Wait, how did you go from P equals N to,
Well, I mean, I say, well, just
oh, 1 equals, never mind.
what
I got
number
it.
is the probability assigning to each of them? It's assigning the same number. That's all I know when I say equally likely outcomes. Yes. So then a probability of S is 1, but it's also the sum of the numbers P. So and those numbers P add up to P times n. So that means solving algebraically, P is 1 over n. And this tells me right away that the probability of a subset E of S is just the number of outcomes inside of E divided by the number of outcomes in S. I just count how many universes are there that satisfy property E and divide by total number of possible universes. So here is an example. If 2 dice are rolled, what is the probability that the sum of upturned faces is equal to 7? Okay, so clearly when 2 of them are rolled, I have this sample space where you have first die is one of 6 numbers and second die is one of 6 numbers. Do you agree? So altogether, I have 36 possible universes. Now I want the universes that give me a combined number of 7. So here is my Kafka protocol, guys. Even if the question is very simple, you want to have in your mind the protocol. So my Kafka protocol is, if the sum is 7, how do I count the events E? Well, I have this the result of die 1. If it's K, then die number 2 has to be 7 minus K. Do you agree? Because they have to add up to 7. So in fact, getting 7 is completely determined by the number I place for die number 1. The second is automatically filled. And K is between 1 and 6. That means that the number of outcomes in E is 6. I had this document for calculating the number of outcomes inside of the event E. Now, for the sample space, it's the same 2 boxes, but this number can be K, this number can be J by the basic principle of counting. It's 6 times 6 or 6 squared. So the answer is 6 over 6 squared or 1 over 6. That's the probability, right? So that's why it's already important, guys. So it's not arbitrary what you calculate. Why do you calculate the number of universes divided by total, right? That I hope is clear. Because each universe is giving you the same probability, which is 1 over the total. So 1 over the total added now the number of times the number of universes you have inside of E. Okay, and then just a small remark. Why is it squared? Because this box can be filled in with 6 numbers, and the other box independently for the second die can be filled with 6 numbers. So altogether, by basic principle of counting, 6 numbers, and for each of them 6 numbers, so it's 6 times 6. The basic principle of counting, guys, make sure to review it. If I'm moving too fast, you stay after class and I will talk about it, right? I can be much slower then. Are you with me, guys? All right, and then first I would like to explain what it means. Let's say, Barry, you're saying, yes, Barry, all thinking are good. You got the right result, and it's amazing. I'm just telling you, at least from my perspective, is that once the problems get complicated, it's very easy to doubt yourself whether or not what you're writing is correct. So is there an infallible way of doing those problems? And I think, yes, if you write a Kafka protocol. Guys, so this document, you have to be very clear on what you're writing. You don't always have to write it, maybe on my exam I would prefer, but in general, you should have it in your mind. You should have quotes, and I will show you how I think of those problems at least, yes? And I hope it will help you. So first, in many probability problems, the word random is used. And random, I think, is just indifferent. It means that each outcome is equally likely. Okay, so random is for me synonymous to equally likely. Here is an example, guys, and we're going to solve it several ways. Okay, just to see what can go here. So we have 3 balls are randomly drawn from a ball that contains 6 white and 5 black balls. What is the probability that one ball is white and the other 2 are black? Hey, Joseph, good. All right, guys. Sorry again for the short time slot I gave you, but we have tons of things to cover and the classes are just way too short. So here is what I will tell you. So first of all, solving those questions, it's like doing combinatorial problems from chapter 1 twice, once for the numerator and once for the denominator. And actually, when you do them twice, it actually gives you a lot of more flexibility, and I will explain later on why. So first, let's consider this problem under different assumptions. It's a bit ambiguous. How are those balls withdrawn? Are they taken right away all at once, or you take them sequentially? Do you sample them sequentially? So let's assume that they are sampled sequentially and that each ball is different from another ball. I can always assume that because they are not in the same space. Philosophically, 2 objects that are not in the same space at the same time are different objects. There must be something about them that is distinct. At least that's useful to think in probability. Good. So what do we have here? We have 6 white balls and we have 5 black balls. And I give those balls 2 IDs. One of them is ball ID number, and that's the numbers you see on the top. Yes, and on and below I give it white ball number, and black balls I give them a black ball number. Yes, I explain why I do that because I use Kafka protocols here, and here is the protocol for the numerator for E. How do I count E? In E, I must for success means that what? That I sampled 2 black balls and 1 white ball. Do you agree? That's success here. So in my form, look how I think. Here is the box, and it's a place of the white ball. Did I sample it first, second, third? The white number and the black number is written sequentially. Okay, so for instance, how do I translate this outcome? This outcome is a success, 1 white, 2 blacks, right? Let's say that first came ball number 9, then ball number 3, then ball number 7, and ball number 3 is white. So here you can see this ball has ID number 3, this ball has ID number 3, and this ball has, in red, has ID number 1. Yes. So first I notice where did the white ball occur? It occurred in the second place. So I put second place here, right? I put 2. And then here I put the actual number that came for the white ball. So this tells me what white ball and where it came. And then I see in sequence 3 came before 1. So 3, 1. You understand? I am illustrating, obviously, for this example, some of you have solved it possibly before, but without this way of thinking. But that's the way I would like you to train yourself to think. Okay? That you are seeing a code in front of you, and you are seeing a form, and a formula or whatever it's called, and you can put information in it. And if I look at this code, I should be able to know what actually happened. So I just need to count how many such possibilities are there. How many ways to fill out this form? Well, there are 3 possibilities here for space 1, 2, or 3. So that's why the number 3 is here. There are 6 white balls, so I can put any of the white ball that came, 6 of them. And then for black balls, 5 possibilities times 4 possibilities. So it's 3 times 6 times 5 times 4. Everybody understood what I did? You understood how I use this form to know how to count. This is a success form. This is the combinatorial Kafka form for the numerator, based on the assumption that sampling is done sequentially. And any code that I put here, if I put it correctly, will identify an actual outcome. So this is 3 times 6 times 5 times 4. It incidentally equals to 3 factorial, 6 choose 1, 5 choose 2. And then I can have the document for S. The document for S, I use the population. That's what I for the numerator, I use the respective ball IDs. And for the denominator, I use the population. I use those numbers to describe them, right? The top numbers. So for that, first outcome can be any one of 11, any one of 10 is the second outcome, and any one of 9 is the third outcome. So altogether, the probability of E is number in E divided by number in S, and it's this number divided by this number, and it happens to be 4/10. Yes, and then I tell you again, somebody wrote in the comments, the answer is 6 choose 1, 5 choose 2, divided by 11 choose 3. And here, if you carry out the calculation, you see that's indeed the case. Yes, you can make it look like an answer that somebody gave before. Any questions?
So at the bottom is the probability of any 3 balls, any color, doesn't matter.
Yes, but my point is, look what I did here, right? So for this question,
Right.
You might say it's an overkill, but I'm trying to, if there is anything I can teach you here, is to teach you to think like a bureaucrat, okay? Which in this case is the right thinking, right? And it's going to save a lot of mistakes. It's going to give you certainty if you're able to think this way. You see, and that means that I have to design a bureaucratic form, and if you input the information properly into that form, you know exactly what happened. All right. So here I was methodical. I said, okay, you have those numbers and you have those numbers, and I described how to put information for the numerator and how to do it for the denominator. Right. For the numerator, I use the red and blue numbers. For the denominator, I use the top black numbers. Good, right? So then assumption number 2. In assumption number 2, we assume that sampling is simultaneous. You understand that I right away pick all 3 balls. There is no notion of which came first, which came later. So in that case, I can design the top form. Look at it. I have those. It's not even a full bar to indicate that here I have to put numbers in order, smallest then bigger number, right? So here I will say which white number did I pick, and which black numbers did they pick. So for instance, if I look at the same event, if this is the situation, I will put they are sampled simultaneously, right? So it's not notion that this was second. I will put that ball number 3, red 3, that's the white ball number, and blue 1, blue 3. I put them in order. Yes, and we know how to do this one. This one is just 6 choose 1. There are 6 possible white balls to produce one white ball, right? 6 possibilities for input in here. And how many possibilities here? Well, I need to choose 2 balls. That's 5 choose 2. Do you understand where the 5 choose 2 comes from, guys? I know how to count the number of outcomes in the second box. 5 choose 2. So the answer here is 6 choose 1, 5 choose 2. And for denominator, I also have to keep the same process. Denominator, I pick 3 balls without order, which means the form can look like this. You see? So I have to put the numbers that I picked. If those are the numbers that came out, I use the population ID and I put it in order. So I put 5 first, then 6, then 10. 5, 6, 10. Good. And so now I have that the probability is 6 choose 1, 5 choose 2, 11 choose 3. And the answer is again 4 over 11. You agree, guys, that we solved 2 different problems. We solved them with 2 different assumptions and the solutions are the same. Why is that? They are not modeling the same process. Yes. Why is that? Now, the reason is, of course, guys, that we're using quotients, right? We're using quotient, numerator divided by denominator, and quotients of 2 different problems can produce the same result. You understand? So so when I carry probability questions, I can often switch from one setup to another setup without affecting the final outcome. So for instance, here we can observe that sequential random sampling generates the same probabilities as simultaneous random sampling. We can observe that in general, and we will do that now. Are you ready? So you saw before we did it sequentially, and then we did it simultaneously, and we saw the same result, and now we can make it into a law. We always will see the same result. So here is a simple example. So here we have a bunch of balls. And let's say the success I'm interested in is in selecting ball number 1 to all the way to R. Yes, all the way to R. So the probability of simultaneous selection of having 1, 2, and R, it's 1 out of all the possibilities. If I choose R of them, all the possibilities are N choose R. Do you agree? Right, so the probability I picked balls that are labeled with the red numbers simultaneously is 1 over N choose R, because I could have picked simultaneously any choice of any R balls. Yes, now what is the probability if I did it sequentially? If I did it sequentially, now to pick balls numbered 1, 2, 3 R means that I could have picked them in any order. There are factorial ways of picking them up. Right, and if I picked any other grouping of R, I could have picked them in any R factorial way. So N choose R times R factorial represents picking in order, and you can see that the R factorials, they cross out. Do you understand? So the sequential in the sequential situation, the number of universes is bigger by a factor of R factorial, but the set E of interest is also bigger by the same R factorial, by the same proportion, and you can cross them out. You understand why I could actually switch from assumption 1 to assumption 2 without anything affecting anything? Yes? Good. So P simultaneous is the same. Very good. Good. So here is another question. A committee of 5 is selected from a group of 6 men and 9 women. If selection is made randomly, what's the probability of 3 men and 2 women? Would you like to answer it before I do? Go ahead, calculate fast. All right, we have 5 solutions by now. All right. Do you hear the noise? Yes? You hear it? Yes, they're trying to break through the door now.
Yeah.
FBI, I think. So yes, let's see this situation, guys. So here we have what? Here we have the first of all the sample space. Sample space. I have 6 + 9 people, and I have people ID. And I also have female and male IDs, right? Just like with the balls, I have 2 numbers. On the top, I have people IDs, 1 through onwards, right? And then red numbers and blue numbers. So for instance, if this situation happened, right, then I just put them in order, you know, from smallest to largest. Those are the people selected. There are 6 + 9, choose 5 possibilities. Then I for the success event, I need 3 men and 2 women. So here is the formula for the document. I put them in order. So let's say this is the actual event that happened, and I see that we have the men are men person number 4, person number 2, and person number 5, and they have those blue numbers as their IDs, and I put the numbers in order. And I put the female numbers in order. And so I have 6 choose 3, 9 choose 2. And I multiply them and I divide by 6 + 9 choose 5. And that's the desired result. Make sense? It's an easy question, guys, but here is how I think of it. And as the questions get harder, hopefully that type of thinking will help you here and there. Okay. So, and of course, making a clever choice for the sample space can drastically reduce the complication of the problem. Do you want to do it today, guys? We have 5 minutes more, or maybe I can, if I stretch it to 10 more minutes, I can maybe finish this question. What do you want? Okay, guys. So this is the idea. If you have to leave, I am not going to be upset, at least not visibly. I'll be thinking about it as I go to sleep. But yes, but we'll try to finish this, okay? So here is a simple example. Imagine that there are n balls in the urn. 1 ball is maybe golden. And let's say that's ball number n. Good? So what's the probability that the special ball is chosen? I'm going to show you several solutions, and I will show you an easy solution of it, right? So how much flexible can you be here? So let's try to solve it very much directly. So first of all, solution number 1, I'm going to work with sequential sampling. Imagine I pick the balls sequentially. So if I pick them sequentially, my sample space looks like this. The document for sample space looks like this. And it has k factorial and choose k possibilities, because I'm going to choose k balls. And my question is, what's the likelihood I pick the ball that I really like? Yes? So that's how to filter. And then I have the success document. The success document, I decided to make this way. So this box is moment when I pick the special ball. So maybe let's say in this case, it was moment number 2. Here it is. So here's what happened here. And here, the remaining boxes are the relative positions of the remaining non-interesting balls. So here is what might have happened. And the special ball was selected in the 2nd place. And here it records the relative position of everything else. So I can clearly use this document to reconstruct what happened if success occurred. You agree? So then I can count how many ways to fill in this document. There are k possibilities. And here there are n-1 choose k-1 times k-1 factorial possibilities. And so my probability is this number. It's the ratio of the number of ways to fill in formula E over the number of ways to fill in formula S. Good. So look what happens, guys. Look, so this is a very ugly formula. I can right away see I can cancel k minus 1 factorial with k factorial. I get this thing a little better. Then I remember my my combinatorial identities to simplify it further. I know that I can multiply this and that by n. And if I multiply this by n, I don't touch anything in the denominator. I just look at the numerator. And the numerator is the same as k times n choose k. So this is the same as that. And why? Because this looks like I have a committee of size k and a leader. Yes. So how many ways are there to select a committee of size k and a leader? I can either select the leader and then give him the remaining members of the committee, or I can select the full committee of size k and designate the leader. You understand? So this means I select first the leader and I have n minus 1 options, and I adjoin to him k minus 1 helpers. Whereas here I first select all of them, and out of them I designate the leader. So you can see by moving from here to here, I'm able to cross n choose k, and I have the answer being k divided by n. Do you understand, guys? I went through it rather fast. I hope you understand. I'm just trying to finish within 5-6 minutes, as I promised. Now we can carry out the selection simultaneously. So then I don't have those lines are not merged. They are n choose k solutions. And for the space E, I can say I chose the special ball. It's a ball. It's already filled in. And how many remaining balls? N minus 1 choose k minus 1. And I have this formula, and we already observed it to be k divided by n. So you see, but that's not the clever way of doing it. You can obtain k over n in one go. Now here is how. Imagine here is the sample space I can create, guys. Now I don't care about the other balls. All I care about is the space occupied by the special ball. And since every selection is equally likely, the special ball, there's no preference where it sits. It either is in position 1, 2, 3, and onwards, right? So the special ball can be in any of those positions. I think of it as a pass dispenser. And I'm going to grab the first k candies of the pass dispenser. So my sample space is a place of the special ball. In this case, it's place 3 in this picture. And it could possibly be in any of the n places. You know what pass dispenser is? Those things do exist still, yes? You don't know what it is? You have this Mickey Mouse head, you open it up, and there is a spring that pushes the candy up. It's called pass dispenser, last I heard. And I heard it a long time ago, guys, right? You're probably dating me like a tree. How old am I, right? From the 40s, from the 30s. But there was such a thing as a pass dispenser. You trigger, you push the trigger, the head tilts back, and you have a candy pushed upwards. Well, yeah, some people know. All right. So yes, you understand? So it's in here. So yes, you see, we have displacement is any one of the n. So there are n possibilities. How many possibilities are there for success? Any one of the first k. So the answer is right away k divided by n. Do you see what I'm saying, guys? So you have a lot of flexibility, and the reason you have it is because you are taking ratios of desired events by outcomes, and those ratios can be, because you have cancellations, you can actually simplify your universes if you have to, right? With combinatorial analysis, when you do it only for the numerator, you have to be more precise. But if you have numerator and denominator, as long as you are using the same procedure for both, and as long as your idea is clear, you can obtain either a very difficult solution or sometimes a very, very easy one, as this example shows. Good? All right, guys. Hopefully we're moving fast enough. Thank you for waiting. I managed to finish slightly earlier. And if you're tired, good night. read Three Comrades. I advise you. I mean, very good book. Take care, guys. I will stop the recording right now.